Right. Well, good morning, everyone. It's really a great pleasure to be here. So thank you to Sadanan for this opportunity to come and present to you some of the work we've done to essentially bring the joys of programming embedded system to all of our undergraduate students in the engineering course of Cambridge University. So before going a little bit further, so I just would like to focus a little bit on what we try to achieve with this cohort. So essentially, so we get every year a group of 350 new undergraduate students. So it's a fair amount. You know, there are bigger courses, but it's actually quite a fair amount. And what they come to do with us is really focus on what we call general engineering. Okay, and so what this means is that at the point of entry, the students don't have to specify any particular interest. We are going to train them to become whatever they want. This could include bioengineering, chemical engineering, mechanical engineering, electrical, electronics, information engineering. Information engineering is super popular these days, but still, you know, the majority of the students are really doing other things. And so why do we want to keep that focus on general engineering, which is quite unusual actually at the moment? It's because really, you know, we are aware that we are taking actually quite a large number of very good and very bright and self-motivated students. And what we want to achieve, what we want to deliver really is to train those engineers so that they can participate and eventually lead multidisciplinary teams. Okay, we really acknowledge the fact that multidisciplinarity is key in today's engineering. And also we want to make sure that through the course of their studies, by the time they finish in their fourth year, they have all the intellectual ability that is required to handle research output. Okay, we want them to really be actors, take research output and embed that in industry or contribute to research. So that means that we have to cover quite a lot of content in the course. The way it's structured is the following. So it's a 4-year program. The first 2 years, all the students do pretty much the same thing. So they study every discipline of engineering, okay? And this is quite a challenge. This is a very actually heavy program. In years 3 and 4, they may want to specialize. Many of them would specialize in 1 or 2 engineering areas. If they select a consistent set of modules, they may have an additional tag on their transcript to say that they specialize in some ways. But this is really up to them. They could continue with a very diverse mix of modules at that point. Some of our students, for instance, these days, you know, combine civil engineering with instrumentation because they are aware that smart buildings are coming along and they want to be able to deliver this. And in the 4th year, they have also a master's project, which usually takes place in a research lab. So, you know, having said all this, for a very long time, really, the expectation is that the practical skills that they need as engineers, they would get through industrial experience, they would get through spending time actually in industry and working in the field, or they would join student societies. And really there was this assumption that, you know, we don't need to teach them how to do petty things like soldering. They would just get that, okay? And in fact, at the moment, what really we realize is that this is actually not necessarily true. Okay, many students are focusing increasingly on their studies. They really want to get, you know, like a brilliant degree, first-class degree. They're going to focus on whatever brings marks, and doing that, very often actually they fail to get all the knowledge that is required to make actually a good engineer today. So what are the challenges we are facing a little bit with this model? Well, students and employers now, you know, really expect us to provide more work readiness. Okay, so engineers are supposed to be able to work straight away in companies, which was not so much apparently the case a few years ago. And there is also this increasing emphasis on social skills, creativity, which many engineering courses really don't quite capture at this point. So we are very keen actually to really improve this, and we've made actually quite a number of steps already. But really, what are the other challenges we face? Well, we take a very diverse group of engineers. You know, as I said, they don't come, you know, willing to do in electrical engineering, where you can assume that most of them would have done already some soldering before. Okay, some of them have never done that. They come from very different backgrounds. This is a very international group. Their expectations are very diverse. Okay, they're going to aim for a very diverse career path. How are we going to actually cater for all those students? The course is very intense. I don't know if some of you have had experience with Cambridge degrees, but the terms are very short. Okay, we have 20 weeks of teaching. Okay, and it's already packed with all the difficult stuff like thermodynamics and fluid dynamics and all the things that really, you know, capture your brain. So it's very difficult actually to add some of those skills within that time without removing content, and it's as you can expect, a very difficult decision to make for academics to remove the conceptual content. And also technologies evolve quite quickly, okay? So we don't want to invest a lot of time in trying to build something for a technology that may look out of date a few years down the line. So that's the issue in focusing too much on what employers want, is that this is a moving target. By the time we implement it, actually the emphasis may be somewhere else. And then, well, it's not so much a challenge actually, this is an opportunity. So engineering education is changing. I mean, people are really taking note of all those problems. There is a strong emphasis now on project-based learning. Number of universities have embraced this. You don't teach actually courses or classes, you just challenge students to work on problems, and doing so they would actually capture those concepts. We're not quite sure how to do that actually and yet make sure that the students are going to have the same conceptual knowledge in mind at the end of the 4 years. So we try to actually aim for something that's a little bit hybrid. One thing that we've been focusing on over the last few years is really to try to define the sorts of baseline of technical transferable skills that we want our students to have, okay? And our students, I mean all of them, okay? Something that all of them should be able to do. And for some of you who have been, maybe interacting with the makers community, there are lots of make spaces all over the world. Now there are lots of areas where people exchange skills to be able to design and prototype pretty much anything. And this is for us really the spirit we want to capture and bring back to the course. Right, so what do we want to do that? So provide this toolkit to students, give them a little bit more autonomy, initiative, so that when they go to their workplace, they know actually how to do basic things. And so thinking about that, so there are a number of things we've really enhanced in our course recently. So first, we've introduced for them this place here. I don't know if the image is good enough. So it's called the Dyson Creativity Center. It's been funded by James Dyson, as you can imagine. But essentially, this is a giant make space for the students to do pretty much anything they want. They have everything from the normal machining tools to 3D printers, laser milling machines, laser cutting machines, milling machines, and so on. Lots of stuff for electrical engineering as well. And we try to provide training for all those equipment. So now we have actually a lab where students are asked to complete a set of Lego parts. So they're given a kit, but the 2 parts are missing, and they have to use a lathe and a mill actually to design them and finish the kit. And this has been actually a very popular activity because they really make something and they have this feeling of having completed a task. 3D printing, laser cutting, all these things we can do. We've revamped our computing course, moving away from the compulsory C++ course in first year to much more gentle introduction to Python with an emphasis on manipulating data, collaborating, version control using Git. So all these things actually have been really popular with the students. And whenever they were doing internships, the feedback we got is that actually they were more capable as well, which was really great. But then to be able to do this, there was this big missing link here, okay? So the thing we were not really providing that many motivated students know is essentially how to use something like an Arduino and put all those things together to build a device that can perform actually a task. All right, and so everything I'm going to talk about is really about designing this very simple embedded system activity so that they know how to get a sensor, plug a sensor, get the data out of it to automate or do some measurements themselves. Right, so because our course again aims at really very different students, we didn't really want this to be flagged as an electrical engineering activity. It had to fit somewhere, okay, so it belongs to computing in a way. And in fact, it serves actually a very useful purpose there. So they have learned Python already, so they know the basics of algorithmics, of numeral calculations. But there are a few very specific aspects that they actually still do need to understand. So the first one relates to memory allocations, arrays, pointers. What is data in a computer? How is it represented? What are the types of data? What is the precision associated with those types? Other learning objectives we are going to integrate there relate to just any form of interaction with the real world, which is something many of them have never done at that point. Talking about interrupts, buttons, LEDs, how do you manage that from a programming point of view? Managing time and resources, okay, all those questions many of them never thought about yet. Introducing the idea of timers, how to program an event that's going to come in the past, and what could the microcontroller do to achieve that. communication protocols. How do you connect two different devices together? How are they going to exchange information? And how can you make sure that this is going to work effectively? And then two other things which actually are very rarely taught, but are actually really quite difficult. If you get a sensor and you're given a data sheet, actually you need some experience to be able to extract a little bit of relevant information from that gigantic document. So we really wanted to make sure that that was part of the experience, that they had to do that, dissect a technical document, even if what they need is a tiny subset of that information. And then soldering, I'll say a few words about that, but soldering is really one of those basic skills that you would expect that 100% of your students have, but we know that actually some manage to go through 4 years of engineering education without having soldered anything. Okay, it's amazing how you can avoid those things easily, in fact, if you're trying hard. All right. Now, so I mentioned the fact that we want to focus on technical transferable skills. As we were designing those experiments and really to make it more in the spirit of these makers community, it was very important to us that the students will not come to a lab on a timetable slot and do something and then this is it, this is done, they have accomplished the task and they go away. So we've tried actually quite hard to make sure that we do the other way around. We give them some equipment, we give them some simple tasks that they can do with this equipment, and we just enable them to use that equipment to do something else. We don't know what that's going to be. They don't know what that's going to be, but that was really the starting point of this activity, that we had to find a way to equip them with tools we think are relevant. And this is where we've been very grateful to have actually partners to work with. I've been very actually encouraging them to work with friends or even their family, take the stuff away, okay, and share it with others. And then later on, of course, we are going to encourage them to use those hardware for other projects. So I'll give you a little bit more of the details of the tasks we've asked them to handle. But the general presentation is always to set some sort of a challenge, something that we want them to accomplish. I'll give you examples in a minute. And then we provide to them resources where we just tell them, well, these are some of the things you may need to know. Okay, and I think this is important to do it like that because some students are already experts in these sort of things, and they have used microcontrollers since the age of 10, and others have never seen it. And you don't want to be too patronizing with them. If they already know how to do it, let's just let them do that in 20 minutes, and this is done. Okay, but then the others, we want just to take them through this process without making them feel actually that they know nothing. Everything is web-based in terms of the resources, so which means that they have plenty of opportunities to do things in their own time, away. Support is providing through a forum where they can ask questions, support sessions where they can just turn up, okay? But we don't necessarily chase them to get the work done. There is a very light touch assessment. They complete a quiz, which they can do very easily if they have done or attempted the task at least, and they're asked to submit the final code they have produced, okay? We test some of them. But really the idea is to make sure that they all attempted, and in fact they all did fairly well in that. So two questions are already been asked twice. So why ARM? Okay, why Arm Mbed in particular? So we tried a few things. I mean, I used Arduinos for a long time. We have them all over the place in my research lab. It all comes from this challenge we have of having 350 students doing something out of sight. Okay, it needs to be very reliable and needs to actually require very little support from us. So the Mbed interface is really nice. So first, you don't need to install anything. Okay, the compiler is online. You write your code online. You select your microcontroller online. You download the file. Okay, and this is it. So there's no problem of having to update libraries. We don't have to support students who may have a Mac, a Linux, or Windows machine with 20 different versions. So that's actually a big plus for us. When you plug the boards, hopefully many of you know that already, but they just show up as a flash drive. Okay, and so the students know that feeling, okay? They've already plugged the flash drive in their computer. They know what it looks like. The only thing they need to do is take the executable file they have downloaded online and drag it on it, okay? Not a single student struggled with that, okay? And what I thought would be the most difficult thing to get them to compile a simple test code, in fact, ended up being really the easiest task, as it should. The code is fairly clean, okay? Compared to Arduinos, where you have lots of constants defined in all those files. I find actually the Mbed library is a little bit easier to understand. But this is secondary compared to all that. But also it's a little bit closer to industry standards. So if they write in their CVs that they can do Arduino, it looks amateurish. If they say, oh, I've got experience with Mbed, actually looks a little bit better. And this is something we find also a positive aspect. Two negative elements, which I think that's going to be improved necessarily over time. The user base, of course, is much smaller than Arduino's with Mbed. The documentation is sometimes a bit patchy. You usually find the right documentation, not always for the version you want. But like already since last year, a lot of the documentation has been ported to the latest version of the OS. So everything seems to be going in the right direction. It does generate large executable files. Okay, so if students really want to do something on low-cost boards using Mbed, sometimes it's a bit challenging. But all these things, I trust, actually can be really improved within a year or two. Now, so we've received really a generous support from both Arm Education and ST Microelectronics. So they helped us a lot, actually. They provided us with these boards that you see there. They are all Cortex M7, right? Part of the Nucleo 144 range. They have huge number of pins, okay? Like you can do all sorts of things with that. You have an Ethernet port, so it's far beyond actually what we can possibly use at that point. There are really two features we really need, okay, for the activities we designed, is that board should be able to run activities autonomously without any hardware attached to it. So it has a button and it has 3 LEDs, okay? And that's all we care about. I'm sorry. But this is really critical, okay? Just so that you can do something interesting without the need to plug already lots of wires to it. But then what is great about it is that they can start with that, and then there's just plenty of scope for doing something much more powerful with those boards. They're amazing boards, okay? I'm sure many other boards are amazing, but those I've really got to like very much. And they did not break. I mean, not a single report of a broken board. I've seen some with twisting pins and so on. They managed. They managed. So the activity itself starts in a very simple way. Okay, the first thing we want them to do, it's called 0 because it doesn't really count. Okay, they just get the board, they plug the board, they are guided through a very prescriptive tutorial to get something to blink, and that's how it should be, right? With most of those boards, the first achievement. They have learned Python, so we have to give them a little bit of concept about C programming, what are C functions, what are types in C, and so on. And debugging is something that is actually really new. What are errors, compile time errors, runtime errors, and how do you debug if you just have 1, 2, or 3 LEDs, okay? Serial port is something that could be useful, but you already need to know how to transfer data through a serial port. So the ability to break down, even a fairly simple task into something you can check with an LED is something we encourage them to do, and they all find that actually quite enjoyable to have this very minimalistic sort of communication. Some came up with Morse code communications to know what's going on, and so you can be very creative with that. So now just to go back to really the meaty parts of the activity. So there are two challenges we ask them, two tasks. Okay, so one of them, the first one is really focused on arrays, data, interrupts, and timers. So they have 3 LEDs, okay, so we just get them to blink the LEDs in a sequence, red, green, blue, red, green, blue, with a fixed gap in between. There's a button, okay, so whenever they press the button, the color that's currently displayed is recorded. And then they have two options. Either they set the duration of that record, and when it's over, it's just played back. Or for the most adventurous people, they implement a double click. Okay, if they double press the button, then it's going to stop the recording. And then if they want to choose that, they don't know how long it's going to be, so they have to really think about dynamic memory allocation. And we provide them a lot of material that they may want to learn about: arrays, pointers on functions, which are conceptually quite difficult. Okay, I don't think at that point they really have this idea that code is memory. It exists somewhere. Interrupts and timers, right? All those things, come in that activity. And then the second one is really taking them to where we think they should all be. Okay, able to grab a random sensor that talks a protocol they understand, and we picked I2C for that activity. And be able to connect that to the board and make sure they can actually have a nice flow of data with that. So here we give them the component you see there. That's a temperature sensor from NXP, the LM75B. It's one of the standard I2C temperature sensors. You find sample code actually for that everywhere. What we want them to do is configure that chip so that is going to trigger a signal in an interrupt pin if the temperature reaches a certain threshold value. Then record the temperature every second up to that point. And when it's reaching that threshold, just dumps everything, okay? Initially, we wanted to mimic some sort of airbag crash electronics, but an accelerometer is actually much more difficult to handle than a temperature sensor. We may try that actually next year. And so here again, I mean, there are things that are quite new to them. Understanding I2C, okay, is something we really want them to do. I mean, you can find libraries to do that, okay, where you just have nice functions to communicate, but we really wanted them to interact with the signal being exchanged at the bit level. So they don't have to do any bit banging, but they have to shape those numbers they're going to send. And I think this is where the information is, where the learning is. To know what they have to send, they have to extract that information from the data sheet. And again, that's not that easy, okay? So turning a 12-bit integer that's hidden in a 16-bit block and turn that into a floating point number is something that requires a little bit of brain power, and that's what they have to achieve there. And finally, so that's where soldering fits, okay? So they're all given that kit here with some wire. They have to do a little bit of soldering. On the other side of that chip, you have a number of pads to set the I2C address as well. So they just have to handle that. They were given actually lots of tutorials for that, okay? We were taking movies of the technicians doing exactly the same thing in a place where they could do the soldering. We did also link that to their materials course. So believe it or not, the composition of lead solder is very specific, and we give them all the thermodynamics to understand why it is what it is. So we actually link elegantly this to their materials course. All right, so how was it received by the students? So first of all, it really worked in terms of the logistic, okay? So very little support was actually required. The Mbed environment, the Nicolo boards, were just very reliable. And that means that we feel confident we can actually continue to offer this. And then I received a number of emails from students, which is spontaneous emails, which actually really never happens. Maybe just me, but not so much actually. And they were really keen to take something and actually learn from home. And this whole idea that they like technology or learning to be transferable really works. I mean, and they were showing that to their like brothers and sisters and family members. And so that was actually really enjoyable. Many of them really learned the content. In fact, a number of them found a small typo in my I2C bit sequence, which I didn't leave there intentionally, but many of them found it, and actually that was quite enjoyable. That they were reading it, they were trying to understand it, and they found the error. So I trust this is correct now. And the feedback was also actually quite good. So usually when you first run a lab, it's a little bit shaky. I mean, it was actually, the timing was not always great in the delivery of the instructions, but this is nonetheless one of the highest rated activity there. So long-term success, we don't know yet, okay? This was running like that for the first time last year. What we want to know is when the students reach their final years, how many of them are going to use that technology, or how many of them are going to use the same board, or if they use different boards, the same sort of environment or the same sort of technique altogether, okay? So we'll need to assess that actually a little bit further down the line. Okay, and so just to wrap up, so from our point of view, this was very successful. There's a lot more we can do with that. Okay, now that we have some sense for how good the students are, we can actually extend that very, very easily. We have a vending machine where we removed all the sandwiches, and now we start putting some sort of electronics that they can actually get to complement those setups. But more generally, this is really some sort of a milestone at the moment to try to redevelop the course around scale building and general engineering through integrated projects. Okay, so this is what we do well at the moment, and this takes the first 2 years with very little room for the other sides. They do scale building, they do projects, like at the same time as everything else, and in fact, there is very little credit given to these activities. We really want now to really shape the whole curriculum around those activities. Okay, so making sure that we give them the skills as early as possible so that when they do internships, they can really put those skills in practice. And really want to give them, at the end, plenty of time to integrate that knowledge so that they can try their skills themselves through the course. And finally, so something I've learned and actually enjoyed quite a lot trying to put those activities together is that it's a much more authentic partnership with industry when you try to take a technology, work with, Sadanand, Chris, even if we only met on Thursday. But to talk about these products and how the course could exploit these things to deliver a message that is slightly different. It's not about the board, but it's how to use those hardware and the resources available to make to get our point across. And I found that much nicer than having to contact them just to raise money and support some teaching activities or provide prizes to students. So there's something actually much stronger in this sort of link. So we hope very much that in the next few years, we can continue this sort of slow revamp of the course at a very fundamental level, and develop more relationships actually with industry to try to get this working all together. Thank you very much. Chris?